In this lecture, we'll look at some of the objects we'll be viewing with the 60-inch telescope at Mount Wilson Observatory. To begin, we'll organize these objects kind of on three different hierarchical levels. The first kinds of objects will be those like planets and dwarf planets that are found in our solar system. The second kind are objects like stars and star clusters and planetary nebula, things that are found in our Milky Way galaxy outside of our solar system. And the third kind are things external to our own Milky Way galaxy, which are other galaxies and objects called quasars. These three different ways of organizing the universe have different spatial scales. So we can measure distances in light travel times. So, for example, the distance across our solar system is about 10 light hours. So it takes light about 10 hours to go from one side to the other side across the orbit of Pluto. The Milky Way galaxy is much, much, much larger. So it has a diameter of about 100,000 light years. And then when we start looking at our local region of the universe, that has scales of 100 million light years, so about 1,000 times the size of our Milky Way galaxy. Okay, so the first part, let's look at objects we'll see in our own solar system. So there are three objects that we can see in the night sky when we go to the observatory. Those are the planets Mars and Venus and the dwarf planet Ceres. So this map is a map that you'll have with you when we go to the observatory. It shows what the night sky will look like on March 29th or on April 29th when we go. The image on the left is a Hubble Space Telescope view of Mars. We, of course, won't get that good a view, partially because we will be looking through our atmosphere, which tends to blur images out. The second reason is that, of course, there's been a lot of image processing that goes into the Hubble Space Telescope images. So the image on the right is maybe something similar to what we'll see with the 60-inch telescope. Mars has an angular diameter of about 5.7 arc seconds. Remember that the best resolution that our atmosphere permits is about 1 arc second. So this is not that much bigger than the atmospheric limit that we can see through our atmosphere. So we won't make out a huge amount of detail on Mars, but if we're lucky, we might catch a glimpse of the northern polar cap or some clouds or maybe some dark markings on the surface. We'll see. Venus should also be up, but I think it's going to be too low in the sky to actually view through the telescope, so I didn't include a picture of it. However, Ceres is an asteroid. It's also classified as a dwarf planet. It's in the asteroid belt between Mars and Jupiter. So here, the image on the left is a Hubble Space Telescope image of Ceres. And then on the right is what it would probably look like through the telescope. It'll just look like a pinpoint. It'll just kind of look like a little faint star. It has an angular diameter of less than an arc second, so we probably won't be able to see any detail in it. Okay, so the next set of objects are things that are within our own Milky Way galaxy. So these are stars, star clusters, star-forming regions, planetary nebula, and supernova remnants. So we'll go through each of these in turn, and again, this is a map of where these objects are in the sky. So we'll start with the stars. Sirius is the brightest star in the sky. You can find it. It's kind of down and to the left from Orion. Orion's belt points towards Sirius. When you look at it through a telescope, it just looks like a bright star. Again, the angular size is way too small to be able to resolve it. Sirius does have a little companion. So the yellow arrow shows an object called Sirius B. It's a white dwarf star. So a white dwarf is the core of a star that has already evolved and died. So Sirius B, this white dwarf, is orbiting Sirius with a period of about 50 years. It's much, 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 much fainter than Sirius itself, so it's very difficult to see. We may or may not be able to see it with the 60-inch telescope, but if we did, it'd be very cool. In fact, the telescope that we'll be using, the 60-inch scope at Mount Wilson, was used to discover that, in fact, Sirius B is a white dwarf by taking the spectra of the star. It was determined that Sirius B has a temperature of about 90,000 Kelvin. Okay, there are a number of double stars that you can see in the night sky. The middle star in the handle of the Big Dipper is made of two stars, Mizar and Alcor. When you look at them through the telescope, you'll see a little trio of stars, the brightest of which, Mizar, is actually a binary star system. So those two stars orbit around each other once every 5,000 years. And so we should be able to get a nice view of those stars with the Mount Wilson telescope. Another double star is off the handle of the Big Dipper. It's called Cor Caroli. It's an interesting star because the two stars are at different temperatures. So the cooler star glows with kind of a reddish color, and the brighter star is kind of whitish or bluish in color. And a third double star, which is kind of fun to look at, is in the constellation Leo. So it's circled here. When you look at it, it has two stars that are pretty closely separated, which are kind of fun to look at. Okay. Most stars are actually formed not by themselves, but in clusters of stars. So there are two kinds of star clusters. There are galactic clusters, which lie in the galactic plane of our Milky Way galaxy, and globular clusters, which are above and below the plane in the halo of our Milky Way galaxy. So we'll look at examples of each. So the open star cluster, M37 in the constellation Auriga, is a collection of about 500 stars, and it's about 12 light years in diameter. So these open star clusters, again, are in the plane of our Milky Way galaxy, and that's why this image is just filled with stars. It's because we're looking along the plane of our Milky Way, and so a lot of those stars are just foreground or background stars. Open star clusters are relatively young, so this one's about 400 million years old, which sounds old, but when we compare it to globular star clusters in this next picture, globular star clusters formed about the time that our Milky Way galaxy was forming, so in this case about 11 billion years ago. So globular star clusters are very old. They're much bigger. So this globular clusters have, hundreds of thousands, if not millions of stars in them. And they're pretty spectacular to see through the telescope. You'll just see this swarm of stars through the eyepiece. These globular clusters are very distant objects. So the 25,000 light years is consistent with the idea that these things are kind of above and below the center of our Milky Way galaxy. So these globular clusters are, pretty distant. Star-forming regions, the most famous example of this is the Emission Nebula in Orion. So the sword of the constellation Orion is formed by the star-forming region when very massive stars that have just recently formed shine on the gas and dust around them. The ultraviolet radiation causes the gas to fluoresce. That is, it kicks an electron in the gas up to an excited state. As the electron cascades back down, it gives off emission lines. And so the pink glow is due to the hydrogen alpha line that we see in emission. But there's lots of other elements too. So the blue is due to oxygen. There's just like dozens of elements that contribute to the gas that we see glowing. So here's a very simple illustration showing how stars are formed. So the Orion Nebula is an example of stellar birth. So in the center of the Orion Nebula is a cluster of stars that are just being born from the dust and gas in the galaxy. If you could wait a few 100 million years, all of the gas and dust in the nebula would condense down to form the stars, and then the winds from those stars will kind of push back that material around them and clear out a space, and that's when you get an older star cluster where you just get the cluster of stars itself. All of the dust and gas has been used up. Planetary nebula. A planetary nebula is the end result of a low mass star like our sun. So in about 5 billion years, our sun will start running out of hydrogen fuel in its core. When that happens, it'll turn into a red giant. So the star Arcturus in the sky is an example of a red giant star. The outer layers will kind of swell up to be much larger than our sun currently is. And then at the end, the layers continue expanding out into space. And they get so thin or so less dense that you can see through them. They become transparent. And what's left over at the very center of the planetary nebula is a white dwarf. We talked about the white dwarf going around Sirius. This is how that star came to be. So the name planetary nebula is a little confusing. It has nothing to do with planets. It's that when astronomers first discover these objects in smaller telescopes, their kind of round shape made early astronomers think that they could have been planets, or at least that they were planetary shaped. And so that's how they got their name. But again, they have nothing to do with planets. They're actually dying low mass stars like our sun. So the picture on the bottom is the picture of the Ring Nebula, which you can see in the summertime. One of the planetary nebula that are up tonight is called the Ghost of Jupiter. The picture on the left is a Hubble Space Telescope image. The one on the right is something more similar to what we'll probably see through the Mount Wilson telescope. So you'll definitely be able to see that it looks like a little round disk. That again, if you kind of squint, it could almost look like a planet. If you could look closer, though, you'll see it has interesting details like you see on the left. And again, in this picture, you can see that center star there is the white dwarf that was the nuclear burning core of the star. Planetary nebulae are some of the most beautiful and colorful objects in the night sky. Here's a collection of 10 different planetary nebula. These are all taken by the Hubble Space Telescope. Again, we won't see anything that looks like this. In fact, it's very difficult to see color with your eyes when you're actually just looking through a telescope because everything is so dim. You're using the part of your eye that is more sensitive to light, but it only sees in black and white. So when you're looking in low light conditions, you really don't see color very well. So anyway, you're not going to see the color, but you'll see the shapes of some of these things. And again, these are taken by the Hubble Space Telescope, so we won't see nearly this much detail. All right, the final object that we'll be looking at in our own Milky Way galaxy is called a supernova remnant. So when you have a more massive star, so like say 10 times as massive as our sun, it has a different evolutionary path. So it'll turn into a supergiant star, for like Betelgeuse is an example of a supergiant star. It'll then evolving into a Wolf-Rayet A star. You might remember these as having emission line spectra. So that's the way of telling when you have a Wolf-Rayet A star. And then eventually, the core of the star will undergo a supernova explosion. The star will just kind of collapse in on itself and then explode outward and just like blow itself apart. The thing that will be left over is either a neutron star or a black hole, or sometimes it just completely rips itself apart and there's nothing left. So an example of the supernova remnant is called the Crab Nebula, or M1. So again, the image on the left is Hubble Space Telescope image, and you can just see this is just the remnants of the star that just exploded, and this thing is expanding outward very rapidly. So this happened fairly recently. So the actual explosion was witnessed by observers 1,000 years ago in China, and so folks 1,000 years ago saw a new star, a bright star in the night sky, and actually you could even see it in the daytime. And over the last 1,000 years, it's faded, and this nebula, this expanding gas, is what is left over. There is at the very center of this nebula a pulsar, which is a spinning neutron star, and we can detect radio signals from that, but we won't be able to see that with our telescope. Okay, now we're going to step out of our Milky Way galaxy and into intergalactic space and look at what is around our Milky Way galaxy. So it turns out that we live on the outskirts of a super cluster of galaxies called the Virgo supercluster. Galaxies, we won't go into this in detail, but galaxies kind of fall into three different categories. There's elliptical galaxies that are basically just balls of stars with not much dust and gas. There are spiral galaxies like our own Milky Way galaxy that have spiral arms. And then there are barred spiral galaxies that have kind of this bar cutting through the center of the galaxy. And then the spiral arms come off of that bar. Actually, our Milky Way galaxy is an example of a barred spiral. So in the springtime, we are well positioned to look out away from our Milky Way galaxy out into intergalactic space. And so in spring, we have a direct view of this Virgo supercluster of galaxies. And so we'll probably spend a fair amount of time looking at galaxies in Virgo and in Leo. So in this illustration, we are at the center of this kind of 3D map of where our stars are. So the yellow arrow shows our view towards the Virgo cluster. When we're looking towards the constellations Virgo and Leo, that's the direction of that yellow arrow. So here's that area. There's Virgo and Leo. We're going to look at a few galaxies. So the red circle shows a zoom in. This is a photograph now showing just dozens and dozens of galaxies towards the center of that Virgo supercluster. And we'll look at a few of these in detail. The one highlighted is called M88. It's a nice spiral galaxy. You can see the spiral structure very clearly. It's an SC galaxy. This one up here is a barred spiral galaxy. You can see the two spiral arms coming off of that central bar. This one over here is an elliptical galaxy. This is called M87, and it lies at the very center of the Virgo supercluster. So over the last, billions of years, this galaxy has been gobbling up other galaxies around it. So this is an incredibly massive galaxy, probably tens of times larger than our Milky Way galaxy, probably having trillions of stars in it. So it's a little deceiving. All it looks like is this kind of faint glow. but that faint glow is due to an enormous galaxy with just, again, trillions and trillions of stars. At the very center of the at the very center of M87 lies a supermassive black hole. So this is the first image ever taken of a black hole, and it was the black hole that's at the center of M87. The emission that you see here is a false color image. This is actually taken in radio waves of the material that's actually spiraling around and falling into the black hole. So M87 has a jet that is streaming out, and that's due to this gas that's falling into it. All right. NGC 4568 is an interesting object. It's two galaxies that are interacting. So in the Virgo cluster, the galaxies are so close and packed into each other that they frequently collide with one another and form larger and larger galaxies. In Leo, there's three galaxies all together. This is called the Leo triplet. You can see the one on the right is an edge-on galaxy. So you can see that little dark dust lane that kind of cuts through it. We're looking, again, all three of these galaxies are kind of pancake shaped. They're all disk galaxies. But again, that one on the right, you're seeing it edge on. So if you kind of look at a pancake or a frisbee edge on, you can see the dust lanes in the galaxy, which is kind of neat. The two on the left are kind of tilted a little bit, so you're looking at them at above their galactic planes, and so they kind of look more like ovals. M104 is called the Sombrero Galaxy because presumably it looks like a hat. Anyway, it's got a very unusual dust lane, so you can see that dust in silhouette kind of circling the galaxy. Again, that faint glow is just due to billions and billions of stars that are too faint to be seen individually, but collectively they give off the glow of that halo around the galaxy. M64 is called the Black Eye Galaxy because it has a very asymmetrical patch of dust which is obscuring the light from the other stars in the galaxy, kind of right in near the nucleus. And M61 is a galaxy that's probably not too unlike our own Milky Way galaxy. It has kind of a loose spiral structure, spiral arms going around it. Okay, so this is now a galaxy in Ursa Major off the bowl of the Big Dipper, off the handle of the Big Dipper. This is called the Whirlpool Galaxy. And you can see that there's that one smaller galaxy over to the right. That galaxy recently went flying past the main galaxy, and the gravity from that side galaxy is causing kind of shock waves in the main galaxy, causing a burst of star formation. So all those little pink regions are due to H alpha emission, where you have new star forming regions. So each one of those little pink patches is like the Orion Nebula in our galaxy, but much bigger. Here's another pair of galaxies in the constellation Ursa Major. The one on the right is called the Exploding Galaxy, M82. It kind of looks like a cigar. It's another edge-on galaxy. So, it's like looking at the edge of this pancake, but it's actually exploding with star formation. So there's just this huge burst of star formation, again, due to tidal interactions of M81, the galaxy on the left, the spiral galaxy on the left. All right, and then kind of down towards the south in the constellation Corvus, the Crow, are the Antenna galaxies. Here are two galaxies that are, again, in the process of interacting with each other. Here's a zoom in. So again, all of those pink areas are regions where stars are forming. That's where gas in the galaxies is being compressed and forming new stars. Here's a simulation showing one possible scenario of how those two big tidal tails are being pulled off of the galaxies. So as they kind of orbit, the gravity from each just kind of pulls off these tails of stars off of the other galaxies, kind of sending them out into intergalactic space. And so you can see in this simulation, you get these like kind of long tails that match what you see on the left. So eventually these two galaxies and the antenna galaxies will probably coalesce into a single galaxy, and it might settle into either an elliptical galaxy or a bigger spiral galaxy. Finally, the last object is C3 which is a quasar. It's in the constellation Virgo. And quasar stands for a quasi-stellar object. So this thing just looks like a pinpoint of light, looks like a star. But it turns out this is the most distant object that we will look at, or we will try to look at with the telescope on Wednesday. So this thing is 2.4 billion light years away. So many, many, many times farther away than all the other galaxies. So this is an example of an active galaxy. A quasar is a galaxy that has a supermassive black hole at the center. Material is spiraling into the black hole and sending off this incredibly intensely bright jet of radiation beaming out from that black hole. So the luminosity of this quasar is about 4 trillion times the luminosity of our sun. For comparison, the luminosity or the total light given off by our entire Milky Way galaxy is like maybe only 100 billion times that of our sun. So this quasar is, orders of magnitude, giving off orders of magnitude more light and radiation than our entire Milky Way galaxy. And that's it.